All right, make sure everyone's in the right spot. And also, like I said, hopefully everybody's got their access code by now and go ahead and working on this stuff. But if you just got your access code or are working on getting your access code in the very, very near future, I have left everything, the pre-section quizzes and all that stuff open. But let me make sure everyone understands that there's two different types of things on your homework set. You have got quiz. Quiz 1 is section 1.3. Quiz 2 is section 1.4, so forth and so on. Each quiz matches up to a section. Now, there's also homework to be done where you have to certify. This is through the HALK system where you have, you know, with section 1.3, they broke it into two different sections. You got 1.3a and 1.3b, and then you got 4.1, and after a while it'll be 4.1, I mean 1.4, 1.5, so forth and so on. But those are the actual homework sections. The quizzes you're supposed to do before class, and then the sectional homework is actually to be done after class and stuff. I have left everything open because people are still trying to get into this class and stuff. So I've left everything open until Wednesday. Wednesday is when things are going to start closing. Why Wednesday? Drop ads done, so nobody else can add the course, so then I can actually start getting the things due date. But for right now, I've left everything open, so if somebody comes in or still having access problems, you can still access everything. Nothing has been closed out on you guys on that stuff. Also, I want to point this thing out for you guys. Well, I'm also trying to find ways of trying to help you guys out at every possible way that I can, and so is the university. But in here, our class meets Mondays and Wednesdays from, 3:30 until 5, something like that. But then it's Mondays and Wednesdays. But I also have set up, it's not required, it is strongly suggested you show up, and that is math review sessions. But you guys don't want to be out here until 5 o'clock on Friday, so I've got this room reserved between 12:30 and 1:45, so it's just like a 12:30 class if you can make it, here in Fretwell 100, where and we're going to start this Friday, where we're going to start going over some of those homework sets from the HALK system. So if you have questions or problems, you can't access something or other, or if you want to see some of these problems done and stuff like that, my preceptor Andrew is going to be helping out, and he's going to be basically, it's a review day where we sit there and just do a bunch of problems and stuff. And as we get closer to test time, you know, I'm also going to do a traditional homework. I'm going to actually kind of give you guys some helpful stuff on that particular stuff. And again, I'll probably do that kind of stuff on Fridays as well. So I set up this Friday, so park this in your calendar. This is every Friday, unless I tell you we won't have it on that particular Friday, between 12:30 and 1:45 in here. We've got the classroom reserved so we can go over, especially the HALK system, because I know a lot of folks are concerned about the computer software stuff, and I mean, this is the future, but I'm trying to give you guys time to get acclimated to it and the like. All right, so also last time we finished up the section on properties of exponents, you know, power to a power, you multiply, to like bases when you multiply, you add exponents. Like basis when you divide, subtract exponents, and did the property of exponents and did several problems. But this is still in section 1.3. So if you'll notice, you'll have actually two homework sets in section 1.3, and they're labeled 1.3a, that's on the exponential stuff, and you got 1.3b. Now in terms of pre-section quizzes, we only gave you one. It has 5 questions on it, and half of them are on the exponential properties, other half's on the basic concepts, and again, the goal is basic here, the basic concepts of the scientific notation. So I'm going to start today's lecture with scientific notation, what the HALK system calls section 1.3b. So I'm going to go through section 1.3b and section 1.4 today. So you're keeping up and can pay attention to your syllabus. All right, so here we go. Scientific notation. When you've got a times 10 to the x, where n is a positive exponent, you're going to move the decimal in places to either to the right or to the left. When n is negative, you move it to the left. So you've got this scientific notation where a is going to be a number between 1 and 10. So it looks like this. A is a number between 1 all the way up to, but not including 10, because it's got to be a one decimal, 8 point something. It's got to be a single decimal and then some digits afterwards. And the n is going to be an integer. Now help me out here. What is an integer? The integer is the power. An integer is plus or minus whole numbers, plus or minus 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. That's what your powers are going to be. They're going to be integers, okay? And so with this integer, to go backwards and forwards, you basically move the decimal place so many spots. Now this is scientific notation, and it doesn't matter what your major is, you need to be familiar with scientific notation. Because what it really does is allows us to save a bunch of ink and how many zeros we need to put into this particular thing. For example, this problem right here. Now, let me blow it up so everybody can see it in the back there. I got 2.4 times 10 to the 5th. And we want to write this in decimal notation. The question you need to ask yourself, because this stuff's real easy, you don't need a calculator for this mess, but this stuff's real easy as long as you're paying attention. Look at this problem, 2.4 times 10 to the 5th, and ask yourself one simple question. Is this a large number or a small number? And how do you know it's large? You have an exponent that is positive. When the exponent is positive, it'll be a big number. When the exponent is negative, it'll be a small number, decimal speaking. Does that make sense? So that times 10 to the 5th means I'm going to take this 2.4 and I'm going to move this thing 4 places. Now, which way do I need to move it if I want to make a big number out of it? To the right 5 places, because of that times 10 to the 5th. There's 1, 2, 3, 4, 5. And every time I moved it over, if there's more decimals, you just put a 0 into those little humps there. So what is 2.4 times 10 to the 5th, also known as? 240,000. Does that make sense? Did I lose you guys anywhere? Take a look at the next one. I got the number, trying to go with the concept here, of 2.4 times 10 to the negative 3. Ask yourself, is this going to be a big number or a small number? Small number. And the reason why it's a small number is because the exponent is negative, which means I'm going to take this 2.4, but to make it a small number, I'm going to move the decimal place to the left 3 spaces, because of the 3 right there. 1, 2, 3, and that's where my decimal place goes. So this will be 0.0024. That's what it's equal to. Does that make sense? Which is, tenths, hundreds, thousands, 10,000s. It's 24 10,000ths is what this is. A very, very small number. Okay? All right, now go back the other way. I got 53 million. I want you to put this in scientific notation. To put it in scientific notation, you got basically what you're doing here is a trick of moving the decimal place. Where do I need to put the decimal place on this number such that I actually create a number between 1 and 10, not including 10? Right there between the 5 and the 3, right? So this would be 5.3 times 10 to the, now how many places did I move the decimal place? So there it is. It'll be 1, 2, 3, 4, 5, 6, 7. Now right there, it's 7. But here's where most students will screw this stuff up at. They will think it's negative 7 because I moved it to the left. Don't think left and right moving the decimal place. Think big and small. Is this a big number or is this a small number? Would you like to have this kind of cash in the bank? Yes or no? All right, that would be kind of like a big number. With a big number, I'm expecting to have a positive exponent, right? So how many places did I move? So it'll be a positive 7. 5.3 times 10 to the positive 7. Does that make sense? Versus this one right here, 0.000000, whatever, 86, all right? Now this one clearly is a very small number. To put it in scientific notation, I've got to put the decimal somewhere between a number between 1 and 10. I put it right behind the 8, so I get 8.6. There's my number between 1 and 10. Times 10 to the, how many places did I move the decimal place? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It's 11. But the question is this. Is that 11 going to be negative or positive? And again, don't think right or left. Think big, small. This thing's small. I actually make this kind of interest rate on my bank account, very small. That would be negative. Does that make sense? Getting a feel for the numbers is the key to this stuff. Again, if you're trying to remember move left, positive, right, negative, or vice versa, oh, you'll screw this stuff up for sure. Think big, small. If it's a big number, positive exponent. Small number, negative exponent, and it goes both ways. You know which way to move it if I need a big number. You know which way to move it if I need a small number. That's the trick to this stuff. Now, how do we manipulate scientific notation? 2.8 times 10 to the 5th times 1.5 times 10 to the 8th. The reason why they put this stuff in the exponent chapter is because you are going to manipulate exponents. Basically, what you do here is group together like terms. You know, because A times B is the same thing as B times A. It doesn't matter about the order of this stuff. So to do this problem, this is what you do. You take the 2.8 and you multiply it times the 1.5. You put the numbers up front first. Then you're going to multiply that times, put the 10 times 10 to the stuff. We group that as like terms together. That'll be 10 to the 5th times 10 to the 8th. I'll do it like this. So I'm grouping together my numbers and grouping together my 10 powers. Does that make sense? Now this you just need to multiply. So that is going to be 2.8 times 1.5. And I ended up getting 4.2. Does that make sense? Times 10 to the, and here comes our property of exponents. When I'm multiplying, what do I get to do with the exponents? Add. What is 5 and 8? 4.2 times 10 to the 13. And now I double check it to make sure it's in scientific notation. Your number in front should be a number between 1 and 10. 4.2 it is. Times 10 to the, and I have an integer as the exponent. This is the correct answer. Does that make sense? Did I lose you guys anywhere? Okay? Let's do this one. And again, what I'm trying to show you is by hand. Don't worry, I'll show you the calculator in a second here. But let's do this one by hand. I got 3.2 times 10 to the 6th times 2.3 times 10 to the negative 4th. Well, again, putting it together, I put my number part out front. 3.2 times 2.3 times 10 to the 6th times 10 to the negative 4th. Now I'm going to put those two numbers together. What is 3.2 times 2.3? 7.36 times 10 to the, what do I do when I multiply? What do I get to do with the exponents? Add. What is 6 plus negative 4? 2. And this is my answer in scientific notation. But, then that's what they wanted, because it said, give the answer in scientific notation. But let's say, for example, on this problem, I want you to put in decimal form. What is 3.2 times 10 to the 6th times 2.3 times 10 to the 4th? Well, it is 7.36 times 10 to the 2nd, but that's a positive exponent, so this number should be big. So which way am I going to move my decimal place? To the right, 2 spots. When I move it to the right 2 spots, what do you get? 736. Does that make sense? I lose you guys anywhere. But this is scientific notation. This is what they call decimal notation. And if I was going to do it on the calculator, and I brought a TI-83 because I borrowed it from David up here. All right, because I left mine in my office, just sitting there right beside the book. That's exhausting. All right, but I want to show you TI-83, 84. It's the same calculator. 84 has just got more memory, looks a little fancier with the rounded edges, but it's the same calculator. And buttons are located in the same spot. How do I double check my answer on this thing? Well, how do I put in 2.8 times 10 to the 5th? Well, there's 2 ways. You can type in exactly the way it looks, the beauty of this calculator, 2.8 times 10. The power button is a little private caret symbol right there, raised to the 5th. And then you got parentheses 1.5 times 10 to the power 8. Again, the little caret sign is your power button. Okay? So you can type it in just like it looks, but the calculator is going to give it back in scientific notation, and it does something special. It has this little bold and a large E. That's the symbol for scientific notation on calculators and computers these days, a bold and E. So let me hit the answer, and what do you see? 4.2e, that bold and E, 13. What does that bold and E stand for? Times 10 to the, it just abbreviates it for me. And so, and you'll notice that's exactly what we got. 4.2 times 10 to the 13th, but that's how you write it in. If you want to actually write it in exactly with the E thing, you have that button, it's called double E. EE right there, that's your symbol for scientific notation. So I could have put in parentheses, you can see it, 2.8 EE is the second function, so I'll go second EE, and the E pops up just like in scientific notation, but don't put the times 10 to the mess in there. You just do the power, 5, close parentheses, times open parentheses. It is 1.5, again, scientific notation, EE, and puts the bold and E up there, 8. It's the same thing, and there you go, 4.2 E13. Does that make sense? Just know your calculator. So not too bad, but that EE button is your scientific notation, or literally if you type it in exactly the way it looks, but just remember that E does represent times 10 to the. Section 1.4. All right, section 1.3, the big part of section 1.3 was working off those exponential properties. And they're going to try to drum that stuff home to you. Exponential properties are very, very important. But section 1.4 deals with something similar, but yet different, called properties of radicals. Now, you guys should be familiar with the famous square root. And this is one of our common properties here. If I have the square root of x times y, that's equal to the square root of x times the square root of y. And if I have the square root of x divided by y, that's the same thing or equal to the square root of x divided by the square root of y, provided the denominator y is not equal to 0. So, in English, let me tell you what the property is. Through strict multiplication division, you can bust up radicals. If you've got one big radical, you can rewrite them as a product or a quotient of multiple radicals, as long as it is strict multiplication division. Addition, subtraction, you can't do this. I wrote it down here. There is a property. The square root of x plus y is not the same thing as the square root of x plus the square root of y. You don't get to break up radicals over addition, subtraction. Only strict multiplication division. Okay? The other property is this, as I'm writing this stuff up here, is this. And just to write it up here for your benefit, this is called the nth root of x. When it's a square root, that's so common, we don't put the 2 on there. But if I wanted a cube root, I would have put a little 3 inside the little v part right here on your radical. If I wanted the 4th root, I put a 4. On the 8th root, I put an 8 right there. So you can have any kind of radical you want. Remember, what exactly is a radical? Well, the square root of 25 is 5. Why? Because to go backwards, the opposite of square root is squaring it. 5 times 5 is 25. The cube root of 8 is equal to what? 2. Reasoning? 2 times 2 times 2. It took me 3 2's multiplied together to get back to 8. So the cube root of 8 is 2. So it's the opposite of the power is these radicals. Does that make sense? So, but here's the connection between the two. We are beating you guys to death. If you look at that section 1.3a, reminding you, because it's a big review, about property of exponents. Power raised to a power you multiply. When you're multiplying like bases and they got powers, you get to add the exponents. When you divide like bases, you get to subtract the exponents. All those property of exponents. You can write radicals as exponents too. The nth root of x is the same thing as x to the 1 over n power. It becomes fractional power. So when you got fractional powers, you really have radicals. But because you have so many properties of exponents, sometimes it's easier to write the radicals as exponents so you can use all your exponential properties and get the answer as quick as you can. Okay? So, that being the case, a little side note here. What is the square root of x also known as, if I want to simplify that? X to what power? Which power? It's 1 over the radical. This is a square root, so your radical is a 2 radical. So this would be 1/2. A 1/2 power is a square root. A 1/3 power is a cube root. A 1/4 power is a fourth root, so forth and so on. Does that make sense? A 1/2 power is a square root. This is going to be something that's going to be very important in your future, not just to clean up algebra, but my ultimate goal is to also prepare you guys for calculus, for those who have to take on the calculus. And you're going to be using a lot of stuff with radicals, and what you want, first thing you want to do to radicals is rewrite them with fractional exponents. A square root is 1/2 a power. A cube root is a 1/3 power. I'll write that one up there. Cube root of x is the same thing as x to the 1/3 power. The nth root, whatever the n is, nth root of x is the same thing as 1 over n power. And because of that, you have some of your famous properties still holding. Remember what to do when you have a negative exponent. Where do negative exponents get to go? On the bottom. So if I have x to the negative 1 over n power, it's a negative exponent. Where's it going to get to go? Same properties of exponents still hold. It goes on the bottom, becomes positive. This is 1 over x to the 1 over n, but a 1 over n power is also known as an nth root. So x to the 1 over n power is the same thing as 1 over the nth root of x. You can go backwards and forwards between radicals and powers back to radicals when those powers are fractions. This one right here is another big property. The x to the m over n. You've got a combination of powers and denominators. You've got a fractional exponent. When you have a fractional exponent, the power in the denominator is your radical. The numerator power is the power on the actual term. So in other words, x to the m over n power is the same thing as the nth root of x to the m. And it doesn't matter how you write it. You can write it as the nth root of x to the m, or you can write it as the nth root of x, the whole thing raised to the m power. It's the same thing. But you want to use whatever version helps clean it up easier for you. Okay? And please remember this. Only through strict multiplication division can you bust up radicals. You cannot do it through a simple addition subtraction. Okay? So some simplifying properties here. What is the nth root of a to the n? Well, according to this, you get a. But the reason is this. All right? For example, if I wanted the square root of x squared, well, the square roots and squares end up canceling, you get x. The nth root and the nth power are opposite of each other. They're inverses. They kill each other off. They cancel each other out. So the nth root of a to the n is just a. And of course, this is your other property that we just talked about. The nth root of a to the m is the same thing as m is your power, so it goes on top. N is the radical, the nth root, so that goes on the bottom. That's a to the m over n power. So let's use some of these properties and let's clean this stuff up. What is the cube root of 8 cubed? 8. And again, the purpose is not to actually crunch this stuff out. What is 8 cubed? Well, 8 times 8 times 8. What's that? I don't know. I got to look it up. 8 cubed is 512. That's awesome. 512. And then you take the cube root of 512, and what do you get? 8. Well, that's just too much calculator work to me. What they're trying to get you to do is recognize properties. Powers and radicals are inverses. They're canceling each other out. The cube root and the cube power cancel each other out, you get 8. Similarly, what's the square root of 3 squared? 3. Well, this one is a little bit easier for me to do for you guys. Let's just crunch it out by hand. What's 3 squared? Work the order of operation inside parentheses. 3 squared is 9. What's the square root of 9? Yeah, exactly, 3. But I'm not actually going that route. That's just way going over the hill here. All you got to do is remember, the radical and the power end up canceling each other out when they're the same. That's a square root, and that's a square. They cancel each other out. So similarly, what exactly is this guy? Let's clean it up. Let's jump the gun here. The fourth root of 81 times x to the fourth. All right, so I'm going to start using some properties. This is strict multiplication. So this is the same thing as the fourth root of 81 times the fourth root of x to the fourth, right? Let's clean up the number first. 81. What do I know about 81? 81 is 9 times 9. Well, what's 9? 3 times 3. So since 81 is 9 times 9, but 9 is 3 times 3, 81 is actually, just to let you know, 81 is 3 times 3 times 3 times 3, right? Which is what? 3 to the fourth. So what I really have here is the fourth root of 3 to the fourth times the fourth root of x to the fourth. Strict multiplication, I get to bust the radical up. Now let's use our property. What's the fourth root of 3 to the fourth? 3, and the fourth root of x to the fourth. And you got your answer. It's 3x. Does that make sense? All right. See if we can make it a little tougher for you guys. What is the square root of x squared plus 6x plus 9? All right, I'm going to write something down. I'm trying to make a joke out of it, but I don't want to insult people, but I will because that's my nature of my job. I'm politically incorrect as much as possible here. Here's the deal. If you do this, the square root of x squared plus the square root of 6x plus the square root of 9, and you tell me the answer is x plus the square root of 6x plus 3, you fail. Why do you fail? Go back to high school, junior high school, or elementary school. We're going to start you all over again. My daughter, who's in kindergarten, you can join her class. All right, so why are you going to fail this class and every other class that follows this? What rule did you majorly violate from this stuff? Lots of them. Thank you. That's true. But the big one is the only time you can bust up a radical is through strict multiplication division, right? What's this crap? That's plus. You can't do pluses. You can't do this. Wrong. So I've got to do something better. I got to clean this guy up. Look inside. This is what they wanted you to do. The square root of, and you need to be able to turn it into multiplication. To turn a bunch of adding and subtracting into multiplication is called factoring. How do you factor? Again, this is looking at it from a review. We're trying to bring back all the stuff you guys did from many moon ago, from Algebra 1, Algebra 2 in high school, so forth and so on. What is the square root of, now here's the deal, focus on this, x squared plus 6x plus 9. The x squared plus 6x plus 9 factors. How does it factor? What times what is x squared? X times x. What times what is 9? That's going to add up to be 6. 3 and 3. And what my signs have to be to get this term? Plus and plus, because that's positive. They have to be the same sign. Since the middle term is plus, everybody has to be plus. And just to prove it to you guys, I'm going to do the full method, make sure I got the same thing back again. X times x is x squared. X times 3 is 3x. 3 times x is another 3x. What's 3x plus 3x? 6x. And last, 3 times 3 is 9. First, outer, inner, last. Does that make sense? I get the same thing back again. But now, let's clean that up. That's the square root of x plus 3. What's x plus 3 times x plus 3, otherwise known as? X plus 3 squared. Because it's the same thing being multiplied. That's what powers do. Multiply the same thing. Yes, sir?
I missed what you did with 6 and 9.
Okay, to do that, what I did was, and I'll just write it up here for your benefit, I took the x squared plus 6x plus 9, and I did what I like to call anti-folding, because it's working in reverse. I'm factoring this thing out. So you have to look at the first term and the last term. What times what is x squared? Is x times x. What times what is 9? Well, we only got 2 factors of 9, 1 and 9 and 3 and 3. But I want to pick the factors such that because that's a plus, it's going to add up to be the middle term. What adds up to be middle term 6? It's got to be 3 and 3. And because this is a plus, these two numbers will have the same sign, they're either both plus or both minus. Because the middle term is plus, that forces both sides have to be plus. Now, that's called factoring. Now, to double check it, you do pull it out. X times x is x squared. X times 3 is a plus 3x. Another 3 times x is another 3x. And 3 times 3 is 9. That's my pulling it out. And you'll notice that I got 3x plus 3x is 6x. So it's x squared plus 6x plus 9, which means that this thing really does factor like this. And since it's the same thing, now let's finish this problem up. Since it's the same thing, the square root and the square cancel, so what are you left with? The answer to this problem is x plus 3. Does that make sense? But again, I wanted to show you this because you'd be amazed how many people trying to rush through this stuff and do stuff like this. Yes, ma'am?
For the last one we did, number 3.
3. Oh, yeah. Yeah.
Would there be a situation where like the number that was in it where 81 was, like would it be able to like be put in simpler like you did with 3?
Sure. And then you would have to leave part of it as the fourth root of whatever's left over, and that could be possibly part of your answer. These problems worked out kind of nice because 81 really is a power of 4. It's 3 to the 4th. But what if it was like, I don't know, the square root of 27? You can bring that up. 27 is 9 times 3. You can take the square root of the 9 part, that's 3, but there's an extra 3 still left inside the radical. So you reduce the radical so it's not quite as big inside the radical, but you still have stuff inside the radical.
So is the goal basically to get it so that it could have an exponent that's the same number as the radical? Like how you put it to the 4th power?
Or try to reduce the powers and the radical as a combination of both of them. Somehow try to get the thing smaller than what you originally started out with. Like, for example, in this problem, I started out with something looking quite nasty, the square root of x squared plus 6x plus 9. But through putting it together and cleaning it up, I could reduce it to something much nicer, x plus 3. The goal is to make this stuff look much nicer. All right? Get my notes up here. Here we go. All right, continuing on with this stuff. Radical expressions and radical exponents. Again, they're really trying to beat this idea, and the whole purpose of this, and this whole purpose is to take radicals and rewrite them as fractional exponents because you got more properties with radicals and you can do more stuff with them when you write in exponential form than you can in radical form. Okay? So, getting used to this stuff here. Like I said, the b root of ax to the a is the same thing as b root of x raised to the a power, which is the same thing as a times, remember the radical is a 1 over power, 1 over the b, and then you can write that as x to the a raised to the b and power to power you multiply, and you end up proving, this actually makes it a proof, that the b root of x to the a is the same thing as x to the a over b. Now, the purpose of all this is to be able to clean up stuff like this and being familiar with property of exponents with this stuff. Now, the first few are quite easy. What is 64 to the 1/2 power? Well, here's the deal. Well, you guys aren't familiar with fractional powers, so you can write them in terms of what you are familiar with. What is a 1/2 power also known as? Square root. So this is the same thing as the square root of 64, and that's something you should know. What is the square root of 64? 8. This one is 8 raised to the 1/3 power. Well, 1/3 power is what in terms of radicals? Square root was a 1/2 power. What's a 1/3 power? Cube root. This would be the cube root of 8. And when I ask you what the cube root of 8 is, I'm really asking you what times what is equal to 8? 2. Cube root of 8 is equal to 2. But then we can start messing you up. What is 125 raised to the negative 1/3 power? All right. There's 2 ways to do it, easy way and a hard way. I think your definition of hard way would be the way I want you to learn this stuff, being able to do it by hand. All right. First off, the first thing that I notice is a big old negative exponent. I don't like negative exponents. Where do they come from? Where do they go back to when I'm trying to clean it up? Since it's on top, you automatically go to the bottom. That's 1 over 125 to the 1/3 power, right? Now, what is a 1/3 power, also known as cube root? So this is now equal to 1 over the cube root of 125. And if you don't know your powers of 125 and stuff, let's just break it down. 125, call the old prime factorization tree here. What times what's 125? What divides into 125? That's pretty obvious here. 5. 5 times what's 125? 125. 5 times 25 is 125. Okay? Now continue to break it down. What exactly is 25? 5 times 5. So officially 125 is 5 times 5 times 5, or 5 cubed. So when you clean this problem up, this is 1 over the cube root of officially 5 cubed, and you've got the cube root and cube cancel. What are you left with? 1/5. All right. Let me show you some subtle differences, because I have some very smart calculator, SAVU technical students in class. This is showing my work. Do you see the work? I see you got rid of the negative exponent. I see you got rid of the fractional exponent as a radical. I see you cleaned up the radical. I see you canceled two properties, and I see you got the right answer. This is what I'll see other students do. Putting on the calculator, 125. Power is the little private symbol right there called a caret sign, raised to the, and anytime on the calculator you got an exponent, you should always put parentheses around it, showing you how to use the calculator. What's my power? Negative 1/3. Oh, these are handy dandy calculators. I mean, there are many computers, they understand what you're asking for. And I hit enter, and there's my answer, 0.2. Or, for those people who love that math fraction button, one of the most important buttons on this calculator, math number 1, convert answer to fraction. What do I get? 1/5. Yep, I got it right. I got 1/5. Does that make sense? But here's the problem. I'm going to see tons of students, they sit there and here is answer, and they're either going to put 1.2 or 1/5, but there's no connection between said answer and said question. So out of a 10-point problem, how many points they're going to get? 0, or maybe even 15 points just for spite. Make me look at crap with no work on it. Show me the work. I want you interested in not just getting the right answer, but the procedure and how you got that right answer. Now, don't give me just calculator answers. Yeah, question. Cool. But if I asked you to show your work, could you go back and use your property of exponents that you learned in this class about negative exponent going on the bottom? Because you had to do that first. And then you're just working the numbers from that point. I mean, you can skip a step if I think, yeah, you really should know what the cube root of 125 is 5. And you can jump from here to here. But if you just got this and then this circle with nothing in between the two, that's what I'm complaining about. I want to see some kind of work. I mean, there are certain things that I expect you can be able to do. You don't have to show me the factorization of 125. I don't need to see that mess. I mean, I understand that, but I'm just trying to show you where the answers come from. But I do need to see this type of stuff. Oh, no. I mean, there's some of the basic numbers. I do expect you guys to know that. But if you don't, you can figure it out. What about this guy? 36x to the 4th to the negative 1/2. First things first. Negative exponents, don't like, get rid of it. So this becomes 1 over 36, there you go, x to the 4th raised to the positive 1/2. And there's lots of different ways I can do this, but I see that 1/2 power. What is 1/2 power also known as? Square root. So this turns into 1 over the square root of 36x to the 4th. And that's strict multiplication, and through strict multiplication division, I can bust up radicals, whether in the numerator or denominator, I don't care. That's 1 over the square root of 36 times the square root of x to the 4th. Okay? What do I get for my answer? Well, this is 1 over, what is the square root of 36? 6. What is the square root of x to the 4th? X what? X squared. And there's my answer. But it's that last part that people started to hesitate on me a little bit. I want to talk about. Okay. There's a couple different ways you could have done this problem. So I got some room right up here. So I want you to take this. Let's just focus on this. The square root of x to the 4th. I want to show you 2 different ways of getting this answer, why they're important. And it's a understanding and comprehending both ways of doing this problem. All right, so I've got here the square root of x to the 4th. Now, what exactly is x to the fourth? It's x times x times x times x. 4 times. I got 4 x's being multiplied together. Understand when you're asking about a square root. When I'm asking about a square root, that means I want to know what times what is equal to that particular number. But in terms of cleaning up square roots is for every pair I have underneath the radical, I get to pull one out. Here's a pair of x's. For every pair underneath the radical, I get to pull one out. Here's another pair underneath the radical. I get to pull one out. And what is x times x? X squared. That's why x to the fourth is x squared. For every pair on a square root, I'll get to pull one out. If it was a cube root, I don't group pairs, I group 3 things together. For every 3 things I have multiplied together, I get to pull one out. Fourth root is every 4 things that are multiplied together. So based upon this concept, if I ask you, what is the square root of 27? What's the answer going to be? Simplifying the radical. This would be the square root of, break down 27. What times what is 27? Well, it's 9 times 3, which is 3 times 3 times 3, right? So, on this particular example here, the square root of 27, for every pair, I get to pull one out. But there's an extra 3 left inside the radical that never paired with anybody, so he just stays there. That's okay, you'll have this stuff later on. That'll be 3 square roots of 3. But we, as mathematicians, define this to be a simplified version of the square root of 27. Does that make sense? All right. Another way I could have done this problem is this. That the square root of x to the fourth, and what they're really trying to show you in this particular section is this. I want you to take a square root and put him back in fractional exponents, because exponents are awesome because you got so many properties. What is a square root also known as? Square root is also known as a what kind of power? Half power. So this is x to the fourth to the half a power, right? But according to my exponential properties from chapter 1.3 stuff here, power raised to another power, what do I get to do with the powers? Multiply. So that'll be x to the 4 times a half. What's 4 times a half? So it's x squared. So there's 2 different ways of simplifying it to get to the same answer. You can use the property of exponents with fractional exponents, or you can do the understandable what exactly is a radical and how do I clean up a radical method. You'll get the same answer, but it's up to you on cleaning it up. All right? What about this guy here? 27 to the 2/3 power. First off, I want you to write it down. This is an important problem here, but I'm going to show you how to write it down. I can write it down 1 of 2 different ways. This is a radical here. You with me? So I can either write it as the cube root of 27 squared, or I could write it as, let's see here, 27 squared cube root. I can either put the power on the outside or the inside is my point. Which one is better? There is one that's better than the other. Which one's better? The one that cleans it up quicker. What do you know about 27? Can you square 27 quickly and then take the cube root of it? No, that sounds like a long road for me. Can you take the cube root of 27? Can you take the cube root of 27? Yeah, what number is that? So putting the radical on the inside of this, putting the radical on the inside makes this would be faster because you can do the cube root of 27, which is 3, and then you can square it, which gives you what? And the answer is 9. And of course, I mean, if I'm going to let you use a calculator, I want to see some work on this thing, but I am going to definitely double check my answer. 27 raised to the 2/3 power, 2 divided by 3. And notice I put parentheses around my exponent on this thing. And when I hit enter, yep, I got 9. I know I got it right. Does that make sense? But this shows my work. What about this dude here? What is 16 raised to the negative 3/4 power? First off, it's a negative exponent. Don't like them. Where do they go? Where do they come from? Get them back to it. Where do they go? on the bottom. This is 1 over 16 to the 3/4 power. And again, this will be 1 over, and it's your choice. Personally, I think if it's a nice number that I'm familiar with, I want to do the radical first, and then I'll power them up. But you can go either way. So I'm going to do the radical first. The 4 is in the denominator. That makes it the 4th root of 16, and then I'm going to cube it, the numerator, power it up. What exactly is the 4th root of 16? What times what times what times what is 16? 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. So the 4th root of 16 is 2, and then you're cubing it. 2 cubed is 8. The answer is 1/8. And again, you know, we all make careless errors, so I want to kind of double check that on my calculator. 16 raised to the -3 divided by 4 power, typing in the negative with it, and notice I get 0.125, and for those math fraction fans, yep, answer's 1/8. Does that make sense? Okay? Again, getting into what I just showed you a few minutes ago about, some of the problems we've done thus far, they've been really nice. The square root of 64. Yeah, I love those. Okay, but what about things like the square root of 800 and the cube root of 1,542, things like that? How do I simplify those type of things? Remember what we call the product and quotient rules with radicals. Only through strict multiplication division do I get to bust this stuff up. Break it up into square roots of the numerator, square roots of the denominator, or square roots times square roots. But it's got to be strict multiplication division inside your radical first. So, if I was going to do this problem right here, I want to clean up the square root of 800, and I want to simplify it. I'm going to do square root of, and I'm going to turn it into multiplication, okay? Or division. This thing, 800, is going to be multiplied. Well, let's break it down. What times what is 800? Now, don't think too deep in it. All you need is a product of two things here. How about 100 times 8? Yeah, that's it. Well, 8 times 100 is 800, right? So now, I can break this up. That'll be the square root of 8 times the square root of 100. Now, let's clean it up. Square root of 100 is what? 10. I can go ahead and put that answer there. That's 10. What about the square root of 8? Well, that's a smaller number, but I don't know what the square root of 8 is, but you can take 8 and break them down until you can't break them down anymore. What exactly is 8? Break it down to its basically prime factorization. What is 8 break down? 2 times 2 times 2, right? 8 is 2 times 2 times 2. But remember what we talked about. This is a square root. And with the square root, for every pair, you get to pull one out. So I get to pull out a pair of 2. I got a pair of 2, so I get to pull out 1, 2, square root of 2 times 10 in the back. Now you want to put together your like terms. There was that 10 we held over, and there's a 2 out in front too. So multiply that. What's 2 times 10? So what is my answer? 20 times the square root of 2. And that is the solution. Does that make sense? And you do have stuff left over in the radical, but 20 square roots of 2 looks a heck of a lot better than the square root of 800. It's simplified. Does that make sense? Take a look at this guy. What is the square root of 6x times the square root of 3x? Question first. Yes, ma'am.
How would you check that on the calculator?
Well, to check it on the calculator, basically, because the calculator doesn't simplify radicals for you, you basically just do this. Type in the question, square root of 800, right? And it's going to put the answer, whether it does all radical stuff, is it put it in decimal form. And then you put your answer in, 20 square roots of 2, right? And if I hit enter on this thing, what should I see?
The same number.
The same decimal. I'm afraid that's how you check it. Okay. What about this guy here? The square root of 6x times the square root of 3x. Well, when you're multiplying radicals, you can break them up or put them back together again. Remember, when it comes to square roots, I'm trying to get pairs put together underneath, inside the radical, so for every pair, I get to pull one out. So with this one, I'm gonna write it as one big old square root of 6x times 3x, one big radical. That's one of my properties. I can go backwards and forwards on this stuff. But now, let's break it up some more. What exactly is 6? Break down 6. What factor 6? 2 times 3 times x times 3 times x. Right? I have factored this thing into its prime factorization, and they won't factor anymore. Now, this is a square root. For every pair, I get to pull one out. It's a 3 and a 3. You see the two pairs of 3s there? Mark them through and pull one out. I've got an x and an x. For every pair, I pull one out. Has everybody been pulled out of the radical? Nope, there's still some stuff left over. What's left over? Square root of 2. So the answer is 3x times the square root of 2. Yes, sir?
Wouldn't the 3x go inside the radical in the previous question?
I'm sorry.
Let's do inside the radical for 20 square root of
20 square roots of 2. The 20 is on the outside, the square root of 2 was left over. Because those pair of 2's came out, and I just put this 10. It's not inside the radical. This guy was outside, so I just grouped him out front and put him with the other 2. That's where the 20 came from. Okay? So this 10, don't be, I kind of cut him off there. It's not part of the radical. That 10 was that guy that squared of 100 I cleaned up first. Yes, ma'am.
How is it that with that problem, like, did you have to have an extra 3x for it to like go outside? Like for the last problem, there's an extra 2 for you to put outside, or are you saying like for that pair, then that 2 goes outside?
Well, no.
Does that make sense?
Well, this 2 is, there's no pair of an extra pair for 2, so 2 has to stay where it's at.
I know, I was talking about how for the last problem.
Okay, I have 3 2's. For the first 2 2's, they're a pair of 2's, I pulled 1 2 out, and that 2 remained inside the radical. Okay, and this was the square root of 100, which was 10, so that's outside the radical. The 2 is outside, the 10 is outside, that's where the 20 came from, outside the radical being multiplied. Try this one. What is the square root of 16x squared? Square root of 16x squared, well, you can break it down into, well, you can do prime factorization if you want to, but I don't think you need to go that far. It's that you can break it down into the square root of 16 times the square root of x squared. That's fine. But you should know some of the basic square roots. What's the square root of 16? 4. And here comes one of your properties. What's the square root of x squared? Squares and square roots cancel. If you wanted to, you can write x squared as x times x, and there's your pair, so it pulled one out, and there's nothing left over. The answer is just 4x. And with these x guys that have variables, you can't check these on the calculator. This is part of that algebra of understanding manipulation. What about this guy here? Well, I think the original problem should have been this. What is the square root of 25 over a 16? But with strict multiplication division, you want to bust that up into the square root of 25 over the square root of 16. But these are some basic square roots you know. What's the square root of 25? 5. And the square root of 16 is 4. And there's your answer. But now, let's start trying to take a look at these a little bit more difficult ones. What is the square root of 18x cubed divided by the square root of 2x? Well, this is division, but a strict multiplication division, you make one big square root out of it, and you can put all this stuff, 18x cubed over 2x, inside your radical. Why do you want to do that? You can clean this up very nicely. What's 18 divided by 2? 9. What's x cubed divided by x, using your property of exponents? X squared. Questions? Does that make sense? All right. Now, clean it up. Square root of, so this now turned into the square root of 9x squared. Well, what's that? Well, you can bust them up again when you want to. That's the square root of 9 times the square root of x squared. And you can clean them up, or you can pretty much skip this step and go straight for the answer, which is fine. I'm just trying to not miss a step, make sure you understand what properties I'm using here. What's the square root of 9? And what's the square root of x squared? So the answer to all this mess is 3x. Does that make sense? Take a look at the next one. What's the square root of 20x to the fifth divided by the square root of 2x cubed? Well, again, if I'm trying to clean this up, I want to clean up all the stuff first inside the radical. So I'll write it as one big radical, strict division, I can do this, the square root of 20x to the fifth divided by 2x cubed. Now, what is 20 divided by 2? So I'm cleaning up inside my parentheses here, inside my radical, 10. What is x to the fifth divided by x cubed? X squared. Okay? Now, because this is strict multiplication, I can break this up. That's the square root of 10 times the square root of x squared. But let's focus on the square root of 10 first. Factor 10. 5 and 2. That's pretty much it. Both of them are prime, so this is your prime factorization. And but there's no pairs. That's my point. There's no pair of 5s. There's no pair of 2s. There's no cleaning up the square root of 10. That's as simple as it's going to get. Does that make sense? But you can clean this up. What's the square root of x squared? X. Squares and square root cancel. So you're left with, you just had to put it back together again, the square root of 10 times x. But the x is on the outside. The square root of 10 is your coefficient in front. Does that make sense? That x is not inside that radical is my point. What's that? You bet. I mean, with numbers, we coefficients, we like numbers out front and variables in the back. But absolutely, if you want an x times the square root of 10, that's perfectly fine. Same answer. Absolutely. All right. So now, after we clean up these radicals, we like what we call combine like terms. Now, you guys have been doing algebra for many, many years now. Here's my question for you. If I ask you the question, what is 5x plus 3x? What's 5x plus 3x? Why? Like terms. X defines the type of function it is, right? And with this, the coefficient out front just tells you how many you got. 5x, I got 5 x's, and I'm going to add them to 3 x's. I got 3 x's. So together, when I put them together, I have 8 x's. So basically, when they're like terms, you just add the coefficients up front. Whether they're x's or some weird square root of 6 or something like that. It could be, as long as the terms look exactly alike, you add up their coefficients in front. That's the pattern. That's what we're doing here. What is 2 square roots of 13 plus 4 square roots of 13? How many square roots of 13 do you have? The coefficient up front tells you the number. I got 2 of them here, 4 of them here. Grand total is 6. And you put the square root of 13 to let you know what kind of stuff you got. I don't have x's in this one. I got square roots of 13. So 2 square roots of 13 plus 4 square roots of 13 is 6 square roots of 13. Similarly, look at this one. I got square root of 5x minus 3 square roots of 5x. What is the coefficient understood in front, even though we don't write it there? How many of them do I have? It's 1. I got 1 square roots of 5x, and I'm going to take away 3 square roots of 5x. So they're the same thing. They look exactly alike. So all I got to do is add up the numbers. What's 1 minus 3? Negative 2, like terms, square roots of 5x. And there's my answer. Does that make sense? Questions? Did I lose you anywhere? All right. All right, then do the next one. What is 4 square roots of 50x minus 6 square roots of 32x? Well, this one you got a problem. What's your problem? They're not alike. So we got to do all that stuff we did before we can combine like terms, we got to make them like terms. So we want to clean this stuff up. So let's focus on this guy. 4 square roots of 50x, right? Let's break down 50. What is 50 equal to? Now I'm going to do what we call prime factorization. 50 is, let's see here, 5 times 10, agreed? And I can break down 10 some more. 10 is 5 times 2, and there seems to be one x. So this thing is just 4 square roots of what's inside there? 5 times 5 times 2 times x. I'm cleaning up just the first term. Does that make sense? But it's a square root. For every pair I have underneath that radical, I get to pull out one of them. What do I get to pull out? So a pair of 5s, the square root of pretty much that's 25, I get to pull out a 5. In combined like terms, what is 5 times 4? 20 square roots of what's left underneath that radical? 2x. That's the first term. I had to clean it up. Does that make sense? Minus, let's focus on the second term. I got 6 square roots of 32x. I'm working on that radical. What times what is 32? How about 8 times 4, right? Okay. 8 times 4 is 32. So this is 8 times 4. You with me? I can break down 8, and I'm going to do this for your benefit, as 2 times 2 times 2. I'm going to break down 4 as 2 times 2, and there is that x left over. So this is minus 6 square roots of 2 times 2 times 2 times 2 times 2 times x. Does that make sense? And these are being multiplied. It's not 2,200. It's 2 times 2 times 2. But remember, it's square root. And remember, there's lots of ways to do this stuff, but I'm showing you the most direct route. So when they start throwing x, y's, and z's at you guys, you do the same thing, okay? Just like your numbers. For every pair on a square root, you pull one out. Here is a pair of 2's. I pull one out. Here's a pair of 2's. I pull another one out. What am I left with? I'm left with a square root of 2x right here, right? And then I've got 6 times 2 times 2. What's 6 times 2? Times another 2? 24. Minus 24. So, my point to this exercise is that a lot of work just to get the problem in the right fashion. But now, I've got them looking just like each other. So what is this? I've got 20 square roots of 2x minus 24 square roots of 2x. What's my answer? Add up your coefficients. 20 minus 24 is a negative 4. Like terms, square roots of 2x. And there's my solution. Does that make sense? Question? Yeah. What's that now? Oh, absolutely. I mean, I could have broke this thing down as 8 is 2 times 4, and I have a pair of 4s, and that would have been cleaned up. But if you get lost, go down all the way down to that prime factorization where you can't factor anymore, and then you can start yanking a bunch of stuff out. All right, try this one. 6 square roots of 18x minus 4 square root of 8x. Again, got the same problem. They don't look alike. So let's clean up 18. As mentioned before, maybe you want to do these perfect square type things here. So I've got 6 times the square root of 18x. How can you factor 18? How can you factor 18? What times what is 18? In terms of perfect squares, how about 9 times 2 times x? Does that make sense? You're right. It's 3 times 3 times 2. That's fine if you want to go that far about it. But what we were just saying here is you can stop a little short if you see some perfect square roots and start yanking those guys out. So, and this would be, and then minus 4. What exactly is 8? That is 4 times 2 times x, right? 4 times 2 is 8. Now, what I'm saying here is I could go to the prime factorization, but I got it down to the point of these perfect squares. 4s, 9s, 16, 25, 36, 49. These are the perfect square numbers. What is the square root of 9? 3. That 6 is out front, and the square root of 2x is still there. What's the square root of 4? 2. So this gives me 4 times 2 times the square root of 2x. So what's 3 times 6 times 3? 18 square root of 2x minus what's 4 times 2? 8 square root of 2x. And of course, what is 18 square root of 2x minus 8 square root of 2x? 10 square root of 2x. It's that like term. Both square roots of 2x, you just add, or in this case, subtract their coefficients. Does this make sense? And if you needed to, break it down to the prime factorization and then pull out the pairs of, for every pair of 3, you pull one out. All right. Multiplication, division, simplest form of radical exponents. Okay? Well, we've been adding, subtracting, what's left? Multiplying, dividing. We're learning how to do math with radicals is basically it. Add, subtract, multiply, and divide. All right. So, if you've got this problem right here, and that is 2 times the square root of 5 times, parentheses, 4 square roots of 5 minus the square root of 3. And I wanted you to clean this guy up. How would you do it? How would you multiply this stuff out? Well, if I tell you this, and I want you to see a pattern. If I gave you 3 times 2x minus 5, 3 times parentheses 2x minus 5, what do you do to clean that up? You know the word, distribute the 3, right? 3 times 2x minus 5 is 6x minus 15. You just distributed 3 on both terms. We do the same thing whether they got radicals or not. The fact is, I've got this thing right here and a number in front. If I wanted to clean it up, this is a minus with parentheses. I'm going to distribute. This would be 2 square roots of 5 times 4 square roots of 5 minus 2 square roots of 5 times the square root of 3. When you're multiplying this stuff out, go ahead and multiply the coefficients out, and then multiply your radicals, putting like terms. What is 2 times 4? 8. Square root of, now put your square roots together. What's the square root of 5 times the square root of 5? Now you're right, but you're jumping the gun on me. I'm trying to show you in case they don't match up. Square root of 5 times square root of 5 is one big square root of 5 times 5, which is 25. You're right, I can clean that thing up here. Minus 2, and what's the square root of 5 times the square root of 3? One big square root of 5 times 3, which is 15. But I can clean up square root of 25. What's the square root of 25? 5, but you're still multiplying it times 8 out front. What's 8 times 5? 40 minus 2 square roots of 15. Does that make sense? Can you clean up the square root of 15? Well, 15, let's see, factor 15. 5 times 3. There are no pairs looking just like each other that I can pull out front. Does that make sense? So square root of 15 is the best I can do. That is my answer. The answer is 40 minus 2 square roots of 15. Does that make sense? And because there's no variables on this thing like an x, I could use my calculator to check this thing out, but the way you check it on the calculator, I'm afraid, is typing in exactly the way it looks. 2 times square root of 5 times on the parenthesis there, 4 square roots of 5 minus square roots of 3, close parenthesis for the square root, close parenthesis for that whole term there. And I hit enter for the decimal. And then I type in my answer, 40 minus 2 square roots of 15. And this is how I check my answer to make sure I got the same decimal version. Does that make sense? What about this guy here? 22. I have parentheses, square root of 2x minus 2 square roots of 3. What's that thing out there? Squared. All right, let's remind ourselves of our exponential properties. Only through strict multiplication division do I get to distribute powers. You're right, there's a big old power right there. But I do not get to distribute this thing. Why not? What's that in the middle of this thing? Subtraction. It's not being strict multiplication division. What does square really mean? Multiply by himself. So this would be equal to the square root of 2x minus 2 square roots of 3 times the square root of 2x minus 2 square roots of 3. Exactly. What method do you use when you multiply term plus or minus term times a term plus or minus term? The famous FOIL, first, outer, inner, last method here. All right, so here we go. Let's see how good you guys are. What is the square root of 2x times the square root of 2x? All right, lots of different things. I get the hard way would be the square root of 4x squared, but can you not clean that up? Okay. Square root of 4 is 2, square root of x squared is just x, right? But this is a property. The square root times the same thing. The square and the square root cancel, so you're just left with the 2x. Here we go. Outer. What is square root of 2x? Remember, the x is inside the radical. Square root of 2x times a negative 2 square roots of 3. Well, you multiply the numbers in front. This is understood to be a 1. What's 1 times negative 2? Negative 2. And then you multiply your radicals. What is the square root of 2x times the square root of 3? One big square root of, what's 2 times 3? 6, and the x is still inside the radical. Does that make sense? Now we're going to go inner. Again, I have a negative 2 square root of 3 times the square root of 2x. That's a negative 2 coefficient in front times an understood 1 coefficient in front. That's another minus 2. And the square root of 3 times the square root of 2x. 3 times 2 is 6. That's the square root of 6x. And then you do last. And when doing last, remember, you multiply the numbers and then you multiply the radicals. What is negative 2 times negative 2? Plus 4. What is the square root of 3 times the square root of 3? Square root of 9, which is 3. And being multiplied, these were the numbers, this was the radical answer. So let's clean this up some more. This is going to be 2x. Now, here we go, combining like terms. This is why they put in this section. What is minus 2 square roots of 6x minus 2 square roots of 6x? How many square roots of 6x's do you really have? Minus 4 square roots of 6x. And then, what is 4 times 3? Plus 12. These guys don't look alike, so that's the best I can do. Does that make sense? All right. Now, one last thing in terms of this, then I'll let you guys go. All right, so far what we've done with these radical terms is we've added, subtracted, multiplied. We actually started out with the multiplication stuff. Add, subtract, and multiply, but the last thing we're going to do here is divide. Because we have something called proper form of mathematics. Officially, you're not supposed to have a radical in the denominator. You need to do something called rationalize the denominator. To make it look good, you don't want radicals in the denominator. So this is all about cleaning up these answers. And basically, it's a game. So if you got 14 divided by the square root of 5, what you're going to try to do is get rid of the radical in the bottom by giving exactly what it needs. You see, you only got 1 5 in the denominator. So how many 5s do I need to get rid of a square root? 2. It needs a pair. So you multiply the bottom by the square root of 5, but whatever you do to the bottom, you do the top. It's a ratio of 1. So this gives you 14 square roots of 5 divided by, what is the square root of 5 times the square root of 5? Square root of 25, which cleans up to be 5. You give exactly what it needs so you can get rid of the radical, and this becomes your answer. We'll study more on this, finish up section 1.4 next time, and then moving on into section 1.5. So you should be finishing up the quizzes for section 1.4 and 1.5 before Wednesday's class. See you guys then.